Good evening. Thank you for joining us on Zoom webinar. I'm Eric Walker, Chair of Highlands Astronomical Society, and it's my pleasure to welcome established club members, new members who have joined over the past month, visitors from our North of Scotland sister astronomy clubs, and to the first-time visitors who have contacted us wanting to find out what we get up to at our monthly club meetings. Tonight's timings, in about 5 minutes time after I finish this intro, we'll have our main talk followed by questions and answers. Around about 8:45, we'll have our club news and astro picks from the month. And about 9:10, we'll have a little wrap up, and that takes us to the close of the meeting. Now, like the last few months, there will be a post-meeting Zoom blether, the link to which will be provided in the chat box near the end of the meeting. And please feel free to come along and have a very, very informal chat with us. As usual, there won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go. Keep yourself connected to the meeting. If you've got any questions for the speaker or the club, please put them into the Q&A section at any time throughout the meeting. If you have any problems, click the hand icon and someone will get in touch with you directly via chat. The chat for general chit chat, I think, will be switched off once we get going, just to minimize any distractions during the meeting. Now, several of you will know we have just held our annual general meeting prior to this main meeting. But if you were unable to attend but want to see and hear what was said, it will be put onto YouTube for members within a couple of days. In any case, it's essential that we can prove to the Scottish Charities Regulator, Oscar, that we achieved an annual general meeting quorum. And we've agreed with Oscar that in the current circumstance, we do this by asking our members to please respond to the email which Rona sent out about a week ago, acknowledging that you've received all the information. You can also take the opportunity to submit suggestions, comments, concerns, constructive criticism for your committee, and it's best if you could do that for us within the next few days, and that allows us to put the AGM to bed. So, what have we been getting up to over the past month? Well, the weather's been pretty good to us throughout March, and we've seen lots of observing activity from our own and affiliated club members. Beautiful photographs of northern lights, the moon, superb deep sky astrophotographs, constellations and asterisms that many of you will be very familiar with. Dave will be showing you a host of these later in this meeting. Our live observing webcasts have again been very successful, and we recruited a new live host who performed superbly. Thanks, Pauline. They're great fun with lots of viewer interaction on the YouTube live chat. And even though the nights are staying lighter now, we plan to run live solar observing webcasts during the day over the next few months. So keep your eye on WhatsApp and Facebook for short notice notification of these events. WhatsApp is continuing to prove popular amongst members, judging by the interaction in the comments we're seeing, and it's now our default method of letting people know what's about to happen. Please contact Lorraine Shepherd, our membership secretary, to get set up with our WhatsApp groups. The all-sky camera continues to provide fascinating star trails and time-lapse sequences, some of which you'll see tonight. This is freely available to anyone to view if you have the necessary web link. I'm personally very interested to see how it will pick up noctilucent clouds in a couple of months' time. Anyway, back to tonight's meeting. I'm going to introduce our main speaker for tonight, Dr. Mark Fox Powell. Mark is a research fellow with the Astrobiology OU group at the Open University. Before joining the Open University in January 2020, Mark completed his PhD at the University of Edinburgh in 2016, and he held a research position at the University of St Andrews for 3 years. His research centres around icy ocean worlds, such as Jupiter's moon Europa and Saturn's moon Enceladus. He's particularly interested in processes such as cryovolcanism, which can bring water from the deep oceans to the surface, where it can be studied by spacecraft. There has been considerable interest in this talk since we posted it on our social media, Mark, and there are a few visitors who have come along tonight to especially hear it. Without further ado, I welcome Dr. Mark Fox Powell and his talk for tonight, Exploring the Ice-Covered Oceans of the Outer Solar System. Over to you, Mark.
Okay, great. Thank you very much for that very kind introduction. I just want to double check that you are seeing my slides.
Yes, we are. Yes, we are, Mark.
That's great. Thank you very much. So it's my absolute pleasure to join you tonight. And what I'm planning to do here is share with you, take you on a tour essentially of what I believe to be, what I think to be are some of the most kind of interesting bodies in our solar system. So we've learned over the last couple of decades that oceans are actually quite common in the solar system. We're really only at the very beginning of the exploration of these. So I think the next few decades are likely to be really exciting as the kind of exploration of these worlds ramps up and our understanding grows. So we're really in our infancy of understanding at the moment, but I think in a way that makes it extremely exciting. So I'll move on to the next slide. Here we go. So just a brief, just to elaborate on the introduction about me, just to kind of tell you where I'm coming from. I have to be upfront about this. I'm not an astronomer. My background is really in kind of the geosciences. I'm interested in kind of geochemistry. It's kind of my background, a little bit of microbiology in there as well. But really what I do is try to interpret or understand observations of other planetary bodies. So this could be Earth-based telescope observations, or it could be spacecraft observations. And I'll give you hopefully some of the flavor of that as we go through this talk. So my work centers around, kind of uses this three-pronged approach where I do experiments in the lab. I use a bit of computational modeling to extrapolate findings from the lab, and then also occasionally visit locations on Earth's surface that have some similarity to another planetary body of interest to help explain these observations that we see. As was pointed out, I spent about 8 years living in Scotland. So whilst I am very appreciative for the kind of new situation that allows a lot more people to join virtually, I very much wish I was with you in person in the Highlands today. Okay, so what I'm going to do first is kind of take you on a tour, a guided tour, more or less, of the solar system's ocean worlds. So to start off, it's worth kind of outlining why we think there are oceans in the outer solar system. So this is just obviously a cartoon of the major planets in our solar system. And what's labeled on here between Mars and Jupiter is this region that's sometimes called the frost line. So in the inner solar system, closer to the sun than this line, water is not stable as a solid. Of course, we see water ice on Earth's surface and also on the surface of Mars and also on the moon in shadowed craters. But if it's sort of exposed to the full kind of radiative power of the sun, it would evaporate. So water is not stable as a solid closer to the sun than this line. But as you go further out, you can condense water as a solid. And in fact, all of these objects, these large planets, the giant planets in the outer solar system, they all have a host of satellites, natural satellites, that have a very, very high content of water. We sometimes call them volatile rich. Water is one of the major volatiles, and it condenses. So you have these bodies that are extremely rich in water in comparison to the inner solar system rocky planets. So here's a kind of an example of some of the icy bodies in the outer solar system. There are some imposters on this picture, of course. We have Earth's moon, which is there on the left-hand side. That's just the scale, to give you some sense of the scale of some of these objects. And we also have Io, which is a moon of Jupiter, and I'll come back to that in a minute, but that also should not be counted as an icy body. But the rest of these are very ice-rich, and we'll be talking about some of them in more detail. You might notice that a few of the names here are in blue. So Europa, Ganymede, and Callisto at Jupiter. We have Titan and Enceladus at Saturn. And yeah, sorry, those 5 are labeled in blue, and that's because we believe that all of them have subsurface oceans of liquid water. So I'm going to start by kind of outlining, describing the Galilean satellites of Jupiter as a kind of archetype for what we think these ocean worlds are. And then we can scale out and think about some of the other objects further out. So the 4 largest moons of Jupiter, discovered by Galileo, are labeled here, roughly in scale with each other and with Jupiter. We have Io, Europa, Ganymede, and Callisto. So these are that is the order in which that is the order of distance from Jupiter: Io, Europa, Ganymede, and Callisto. And there's a fantastic astrophotography image on the right there that shows all 4 Galilean moons as well as Jupiter. So these are experiencing an incredible amount of internal heating. And this arises because of tidal forces. So this animation here is just showing you 3 of the innermost 3 of the Galilean moons. And they are in an orbital resonance. So you can see how for every 1 orbit that Europa makes, Io is actually making 2 orbits. And Ganymede has a 4-to-1 orbit ratio with Io. So for every 4 orbits that Io makes, Ganymede will make 1. And it's the kind of transfer of momentum between all these bodies, the way that they're squeezed and stretched by each other's gravity and by the gravity of Jupiter, that deposits a huge amount of heat energy into the interiors. And in fact, the tidal heating decreases with the distance from Jupiter. And we can actually see evidence for that quite clearly on the surfaces of these bodies. So a lot of what we know about these moons of Jupiter comes from the Galileo mission, which I've got on this previous slide. This was active in the Jupiter system between 1995 and 2003, and has really kind of given us most of our knowledge of the kind of up close and personal information and data we have on these 4 moons. Also, the Voyager 1 spacecraft has provided as well some really great imagery of these moons, but a lot of the kind of geophysical data that has been needed to understand the interior structures of these bodies has come from the Galileo spacecraft. So as we move out with distance from Jupiter, the amount of heat deposited within each of these moons decreases. And you can really see the effects of this if we kind of look at some of them in more detail. So Io, I mentioned earlier, actually has no ice at all. So we think it originally accreted ice, like all of these objects in the outer solar system. It would have condensed a load of ice onto it in its early formation, but because it has so much tidal heating from Jupiter and from the other moons, it is extremely volcanically active, and that heat has essentially kind of boiled off, evaporated away all of that ice and water that would have originally condensed. Io is actually one of the most volcanic, is the most volcanically active body in the solar system. And this is a fantastic series of images stitched together into a short kind of video clip of an absolutely enormous volcanic eruption on the surface of Io. So this is volcanism like we know it. So it's molten rock and volcanic gases that are being spewed out onto the surface. And in fact, the yellow color of Io really is derived from that sulfur, that's the volcanic sulfur that's being delivered from these volcanoes. If we now go to the other extreme, to the furthest moon from Jupiter, Callisto. Now this is the one that receives the least tidal heating. This is an icy surface now, almost pure water ice, and it's very, very heavily cratered. So you can see in this close-up image from the Voyager 1 spacecraft, it's absolutely pockmarked in craters, a lot of these white specks all over it. And in fact, it's one of the most heavily cratered objects in the solar system, which is telling us that it's an extremely ancient surface. There's very little activity happened there. And it's just allowed it to accumulate impacts over billions of years. So things get a little bit more interesting when we kind of move into the middle here and start looking at the two middle moons. So Ganymede first. So this is a planet-sized object. Ganymede is larger than the planet Mercury. In fact, it is the largest moon in the solar system. Titan at Saturn is just a close second. And Ganymede, you start to notice, it looks a bit more interesting. There's something going on here on the surface. It's covered in these bands and ridges and lines. And if you look more closely at the surface, a lot of these kind of cut through terrain that used to be, that was cratered, that is cratered. So this is telling us that this is younger material that has erased some of that older cratered material. So again, it's very icy, but it has this evidence of activity. And that is really a signature of that internal heating that it's receiving. That is powering some kinds of icy geological activity on the surface. And then finally, when we look at Europa, things get extremely interesting indeed. So Europa has a very young surface, almost devoid of impact craters. And in fact, the estimates of the surface age of Europa put it at around 100 million years, which is really young. That's actually younger than a lot of Earth's surface. So this is being actively resurfaced. We have a very complex network of fractures and cracks and lines all over the surface. There's obviously a lot going on here, dynamic, active processes being powered by that tidal heating under the surface. Now, I'm going to come back to talking about the surfaces of these bodies a bit later on. So I'm not going to get into too much detail for now, but instead what we want to do is think about the interior structures of these moons. So based on the fact that they are tidally heated, it was predicted several decades ago that they should have liquid water layers under the surface. Now, this is just based on the fact that you can just do some maths. You can figure out how much heat is being deposited in the cores of these bodies. You can understand the surface temperatures of them based on the distance from the sun. And some simple maths can tell you that there must be, under steady state conditions, a layer of liquid water. But it wasn't actually until the Galileo spacecraft arrived in the Jupiter system that we had a confirmation of that prediction. So this is an image on the right-hand side of Europa, Jupiter's moon Europa, and represented on the picture are magnetic field lines. So Jupiter has an absolutely enormous magnetic field, the most powerful in the solar system, and Europa is interacting with it. And the only way to explain this interaction that you see here, it's called an induced magnetic field. It's the way that these field lines are kind of bent by the presence of Europa. The only way to explain that is if Europa actually does have a conductive, electrically conductive layer in the subsurface. So that really is really strong evidence that there's a salty liquid water ocean in the subsurface of Europa. Now, we also think that based on the density of this moon, and also of Ganymede and Callisto, that they must be a rocky core. So deep down underneath the ice and underneath the liquid water layer, we have a rocky core, not dissimilar from the kind of rocky portions of the inner solar system planets like Mercury. And on top of that, we have these layers of water and ice. And these bodies do have a really sort of significant amount of water. So this is an image here, Europa compared to the Earth. Europa is now to scale with the Earth. So it's about the size of our moon. And Europa actually has, give or take, around twice the volume of liquid water inside it than all of Earth's oceans combined. So that's represented here by these kind of blue balls. And you can see how the volume of liquid water at Europa is significantly larger than that on the Earth. So this is a significant amount of water. And when we consider that Ganymede and also Callisto as well is thought to have a subsurface liquid water layer, we're talking about huge, vast oceans out there in orbit around Jupiter. And that kind of raises this question, where there is water, is there life? Wherever we look on the Earth, the answer to this question seems to be yes. Where there is water, there is life. So the logical extension of that question is, where we see oceans beyond Earth, could there be extraterrestrial life there? So we can actually start to try and answer that, or at least kind of make some educated guesses or hypotheses. And what we need to do is think a bit more about the internal structure of these moons. So these are just very simple diagrams of what we think the internal kind of structure of both Ganymede and Europa look like. And there are some really important differences when it comes to thinking about their potential for life. So on the left is Ganymede. It's just a wedge. You imagine just kind of cut a two-dimensional wedge cut into the moon, reaching all the way to the core. So if we start from the middle, this first bit of the wedge is labeled C. That is the core. And then we have this bit labeled S. That just means silicate. So basically these two bits together are the rocky portion of Ganymede. And then above that, we have the icy, the water layers. But because Ganymede is so huge, it's, as I said, it's larger than the planet Mercury, it has a really high gravity. Not as high as the Earth, but high enough that means we have very, very high pressure at the bottom of the ocean. So you can see these are labeled in terms of their depth. We have an icy shell of around 150 kilometers. And then under that, a liquid water layer labeled with L of about 100 kilometers. But under that is this strange kind of exotic material, which is often called high pressure ice. It's really a solid form of water that only forms at really high pressures. So we don't have really any examples of this on Earth, because when you get up to those pressures, the temperature is in the deep Earth, I mean, kind of in the mantle of the Earth, the temperatures are extremely high. So water is not in this form. But on Ganymede, the temperatures are low and the pressure is high. So we form this this kind of verged form of water, which is high pressure phase. And because we're used to thinking about ice as something that floats, so it would, when you form ice from water, it will solidify and it will float. It will form a crust on the top, and that's indeed what this top layer is. But the high pressure ice layer is actually more dense than the liquid water and will sink. And because of that, we expect that there could be up to 500 kilometers or possibly more of this high pressure ice kind of sealing the ocean away from that rocky core. It acts as a barrier between the rock and the liquid. You compare that to Europa on the right, it's much simpler. It's a much smaller body. We're on the scale of our moon, Earth's moon. And that liquid water layer is directly in contact with the rock. So the C and the S here, again, are the rock, and the liquid water layer is directly in contact with it, meaning that we do not have enough pressure to make this dense form solid water. I don't really want to call it ice because it gives the wrong impression. It really is just a solid type of water. We don't have any of that at Europa. So here's another representation of that. Now the two moons are sort of to scale here, so you can get an idea of how the size of the moon is really one of the driving factors here. And the liquid water layer is labeled with the arrow on both. So actually it's a similar depth on both, but you can see how on Ganymede on the left side, you have really huge amount of this high pressure ice, this high pressure solid water underneath that ocean, so that the rocky part of the moon is miles below, in fact hundreds of miles below the liquid layer. So what does that mean really? So when you have a tidally heated interior and you have liquid water ocean in contact with the rock, you can have hydrothermal sort of water rock reactions going on, chemistry basically. This is just represented here in this kind of simple cartoon. But this kind of chemistry could be very important for driving that potential for life. So on Earth, we see deep sea hydrothermal vents. There's some at the mid-Atlantic ridge in the Atlantic, and there's others in the Pacific, right on the plate boundaries, things like that. We have these features. They often called black smokers just because of the way that they look. They have this black sort of dust sediment coming out of them, really, really high temperatures. And there are whole communities of organisms down there, like these tube worms you can see in the lower image, that survive completely in the absence of sunlight. So the way that works is that chemical energy from the hydrothermal vents is harnessed by certain types of bacteria that live within the vents. And these bacteria then form the basis of a food chain that is completely disconnected from the input of the sun. So unlike pretty much every other ecosystem on Earth, which depends ultimately on photosynthesis, plants or algae harvesting sunlight and converting that into sugars and organic compounds that could be eaten by other organisms, these communities are completely devoid of input from the sun. So that is quite exciting. That raises the possibility. It kind of demonstrates that life can do this. And it raises the possibility that on Europa, a moon that is an object that is clearly very distant from the sun, but also has this barrier between any potential habitat, which is the ocean, and the sunlight. It has this layer of ice that forms a barrier. So in the absence of sunlight, we know that we can have communities of organisms like this. So this has raised a lot of excitement about Europa as a potential for current living extraterrestrial life. And it's worth pointing out actually that its value extends beyond whether or not there is life there, of course, because the answer to that question, if Europa does not have any life, despite the fact that it seems like it may well be habitable, this could teach us something about our origins, about the origin of life on Earth. Maybe there are certain types of chemistry going on in an ocean of Europa that could teach us something about kind of the precursors to biological processes that occurred on our Earth. Okay, so if we move further out now from the sun and we move to Saturn, here's an image of the Saturn system taken again from Earth, and some of its many, many moons are labeled here. The Saturn system is really different to the Jupiter system in lots of important ways. And one of them, really obvious one, is the presence of this very large ring system, which is kind of Saturn's defining feature. This is an incredible image, one of my favorite solar system images actually, taken by the Cassini spacecraft. Cassini is a mission that is really kind of important to me because of a few things. I mean, for a start, my job would not exist if it wasn't for Cassini. It really has kind of opened up the study of the ocean worlds in a way that no other mission has, I would say. But also, I was lucky enough as a child when I was in school I actually lived in California and for a few years, and I was lucky enough to see the Cassini spacecraft in the clean room at the latter stages of its assembly. So it was probably I don't know, about 6 months or 8 months, something like this, before launch, 1995, I believe. So that has, Cassini's been quite an important factor for me. I can't claim that directly inspired me at that moment to end up working in this area now, but there is some kind of a connection there somewhere, and it has always stayed with me, that memory of seeing it. So a fantastic image by Cassini here, showing the ring systems, and actually what you see surrounding the rings, this diffuse kind of cloudy structure, that's the E-ring, and the E-ring we'll come back to in a minute. So there are, out of Saturn's many, many moons, there are 2 confirmed ocean worlds, and that's Titan on the left and Enceladus on the right. So these are roughly in scale with each other. And I'm first going to talk to you a bit about Titan. So you may well know lots about Titan already. It's an extremely fascinating world. One of the main kind of defining features of Titan is that it has an extremely thick atmosphere, and it's the only place in the solar system apart from Earth where you have rivers, you have lakes, you have rain, and all of these processes are happening at temperatures far, far, far below the temperature of your freezer. So this, instead of water, we're looking at liquid hydrocarbons here. So the methane is one of the main components. We have ethane and hexane as well. These are small organic compounds that on Earth are gases, but the temperatures of Titan's surface are liquids. Well, actually sit at this boundary between liquid and vapor, a bit like water does on Earth. And that allows us to have weather and a methane cycle in the same way that we have a water cycle on Earth. So the image on the left is actually an infrared image, and it's looking through the atmosphere of Titan, which is very thick and orange and hazy, so that we can get some idea of the surface. But the image on the right is a fantastic image from the Cassini spacecraft, looking through the upper atmosphere of Titan. You can just see the sunlight glinting off, reflecting off one of its seas, its oceans ocean, it might be a stretch. It's an inland sea, large lake of liquid methane in the North Polar region. So the upper image here is actually an artist's impression of what one of these lakes and river systems might look like. And in the right, and the lower panel on the right, you can see maps that have been built up from Cassini's flybys of Titan, actually mapping out the distribution of these lakes. So these are all, again, liquid methane, liquid hexane, liquid ethane, not liquid water, but they form part of this dynamic cycle on Titan's surface. But Titan is indeed an ocean world in the same respect that Ganymede and Europa and Callisto are at Jupiter. Titan has a deep subsurface layer of liquid water. So far below that surface, where you have the methane and the hexane and the atmosphere, the bedrock there is water ice, which behaves very much like a rock at those temperatures rather than the kind of ice that we would think of. But beneath that, many kilometers beneath that, is a liquid water layer, and that's a global subsurface ocean, just the same as you would find at the Galilean moons of Jupiter. And because Titan is, again, kind of a very similar size to mass to Ganymede at Jupiter, you have this high pressure ice again. So that's labeled on this diagram. In case it's not obvious, that this diagram is just, it's as if you've taken a kind of core sample all the way down into the interior of Titan, and we've pulled it out and we're looking at it. You can see the high pressure ice labeled on here as well. And below that is a rocky core. So it's a very similar interior structure to the Galilean moons, but it has this added feature of having a really dynamic surface environment as well. It's worth mentioning as well that both Europa and Titan are known, the surface, the icy surface, which is a crust of water ice floating on top of a liquid water ocean, is known to be decoupled from the motion of the moon. So as the bodies are in motion around their respective planets, Saturn and Jupiter, the surface gradually drifts in a way that tells us just another level of evidence that there is an ocean there. The surfaces are decoupled from the core, essentially. So then that brings us to Enceladus, which is the other ocean world at Saturn. Enceladus is tiny. It's about 500 kilometers in diameter, so it would fit easily between where I'm sat right here in Milton Keynes in sort of southeast England and the JSL Observatory for the Society just outside Inverness, with room to spare. So it's a very small world, but it's an absolutely fascinating one. Again, we have a subsurface ocean, and possibly one of its most famous feature, it really are these enormous south polar plumes. So you can see them very clearly in this image by Cassini. These were not known to be there, to be in existence until Cassini arrived at Saturn. It was a complete surprise discovery. And these are actually the source of Saturn's E-ring. This is what I mentioned earlier, that diffuse region around the main ring system. That cloud of dust is all sourced from Enceladus. And here is an infrared map, a thermal map of the surface of Enceladus. And you can see how this is just looking at different hemispheres. Draw your attention particularly to the bottom two, looking down at the North Pole and then up at the South Pole. And you can see how that South Polar region is just where a lot of that heat is concentrated. So the heat is being lost in a very sort of asymmetrical way from Enceladus's interior, and it's all kind of being lost out of these vent structures in the South Polar region. There are some similarities here as well with features we saw the Galilean moons, like Europa. We have some kind of cracks and fracturing looking features on the surface. And all of this is being driven by internal heating of a similar type to what exists at Jupiter and the Galilean moons. So we now know, thanks to Cassini, that Enceladus's ocean is a global ocean. It is in contact directly with the rocky core, unlike Titan, unlike Ganymede. It's too small to have enough pressure to generate this high pressure solid water. So we have free interaction between the water and the rock. And we actually know, thanks to Cassini, that we have ongoing hydrothermal chemistry within Enceladus. So unlike Europa, where we can at the moment just speculate about that, at Enceladus we have direct evidence, thanks to Cassini, that there is hydrothermal chemistry. So this is that hot water rock interaction of the kind that we know on Earth can sustain communities of organisms. So then we can kind of look further out into the outer solar system, or actually in some cases closer to home. And indeed, there are many other candidate ocean worlds out there. These are objects where we think there may well be a subsurface liquid layer, some of which might be similar to Ganymede and Titan, might be sandwiched between layers of ice, but others may well be similar to Europa and Europa and Enceladus, may well be free to interact with the rock. And there are a great many of these. In fact, there's more than are just on this slide. People talk about other objects out in the Kuiper Belt being potential candidate ocean worlds. And I think one thing is certain is that if we are seriously considering oceans being present at these bodies, then why not others? If you think about objects, I'll just run through them actually while they're on the screen. We have Triton, which is Neptune's largest moon. It's very cold at the surface. We have predominantly we have a lot of nitrogen ice on the surface, but also water ice, and it seems to be very active, but we don't know much about it. We know even less about the moons of Uranus, but several of these are being talked about as potential candidate ocean worlds, including Miranda and Umbriel and Oberon. Pluto was visited by the New Horizons spacecraft a few years ago, and there's plenty of evidence there for geological activity, for resurfacing, for volcanism, cryovolcanism, as we call it, low temperature ice volcanism. And also, weirdly, the dwarf planet Ceres, which is sat in the asteroid belt, much closer to home. In fact, we're actually at Ceres, we're closer in than that frost line I mentioned earlier. So here we're at a region where the volatiles that would have originally, like water, would have originally condensed onto Ceres, should evaporate away, and indeed they have. But there seems to be evidence of subsurface water at Ceres in the form of volcanoes, essentially, of water and salts that we see on the surface. So there's a whole host of different worlds out there that may have quite large quantities of liquid water in the subsurface. And it makes you wonder if there are so many in our solar system, this may well be a very common feature of the universe generally. And there are plenty of people now working quite hard to try and figure out ways of detecting exomoons, so moons around giant planets in other star systems. And it could well be that there could be a whole host of oceans around other star systems as well. In fact, this may well be the most common type of liquid water environment in the universe. Okay, so that's kind of our guided tour of the oceans of our solar system. So now what I want to do is just outline some of the ways in which we study these oceans, or try to at least. Yep. Okay, so the main challenge we face here is that the crusts, the oceans that we're trying to study, that we're interested in, are locked underneath, in some cases, many, many kilometers of solid ice. So at Enceladus, we have our kind of best guess is that in the South Polar region, we have about 5 kilometers of ice, but that increases up to 35 in the Northern Hemisphere. At Europa, it's anyone's guess, somewhere between 10 and 30 kilometers. And at the larger moons, you're talking hundreds of kilometers of ice. So actually accessing these oceans directly is kind of out of the question. We've tried to drill through ice sheets on Earth with limited success. It's very challenging to do, even on Earth, where you have things like a breathable atmosphere and kind of you can fly in equipment when you need it. And obviously none of that those luxuries are available to us at the ocean worlds. So really drilling through and accessing these oceans directly is pretty much out of the question in the foreseeable future. But thankfully, nature is kind of giving us a way of studying these oceans indirectly. So I've alluded to this a few times already. And this is one of the ways in which Cassini has given me my job, frankly, is by doing a number of flybys, close flybys of the plumes of Enceladus. So one of the ways in which we can study these oceans is actually by directly sampling material like this. So this is just these two images. One of them is a real, on the left is a real image from Cassini, and on the right is an artist's impression of the spacecraft flying through these plumes at a much lower altitude than it actually did, but it looks good in the picture. What it found was a whole population of tiny dust particles, icy grains. So Cassini was actually built in part to study dust in the Saturn system. It has this instrument called the Cosmic Dust Analyzer, and that was able to capture and study particles like this in the plumes. Now, through studying their composition, what they're made of, we noticed that they have a lot of salts in them, and this really is telling us that they are frozen samples of the ocean. They're ocean spray which has been ejected into space and frozen, and now we are sampling it with this spacecraft. but there's a lot of unknowns here, and this is kind of some of the research that I've been doing is trying to understand the processes that go into forming these types of grains and the plumes themselves to help kind of better understand Cassini data. So what I did was experimentally reproduce these icy grains under conditions relevant to the Enceladus plumes, and then use an instrument called a cryo-scanning electron microscope, which is a high-powered microscope that we can use at very cold temperatures that we can actually image ices themselves. And here's just some examples. So these are frozen droplets that have been cut open, and you're kind of looking down at the cross-section of the droplet. And within that cross-section, there's a whole load of kind of processes that have occurred where salts and other dissolved components in the fluid have all kind of crystallized out during this very rapid freezing process that we think is happening at the Enceladus plume. So this kind of work is helping to interpret the data sent back by the Cassini spacecraft. And as we kind of think about other ocean worlds that I've already described, understanding plume formation in this way is hopefully going to help us explore those oceans as well. So Europa, a lot of people think there's a lot of discussion at the moment about the potential for plumes similar to the Enceladus plumes at Europa. These images on the right-hand side are actually from the Hubble Space Telescope and show this transient, what we think is plume activity that kind of comes and goes periodically. Artist's impression on the left. And if indeed there are plumes there, we may well be able to sample them using a similar approach to the Cassini used at Enceladus. We can also do remote observations of the surface. So rather than capturing any samples directly, we can look at it remotely, either with spacecraft or with Earth-based telescopes. And this is particularly useful at a moon like Europa. So here is a fantastic Galileo image from the Galileo spacecraft of the surface of Europa, a region of the surface. And you can see it's absolutely covered in cracks and fissures and all kinds of strange features that are really indicative of this subsurface activity. So to just talk about how we think some of them might form, these kind of blob blister-like features that you see, this one here is circled with yellow, they are called chaos terrain, which is essentially planetary science language for we don't know what it is. Well, they're thought to be cryovolcanic regions. So these are kind of volcanic craters, if you will, that are being fed by localized heating underneath, and there's a good chance there for melt through and transfer of liquid from the subsurface onto the surface. There's also these bands, they're called lineae or linnae, and these are thought to be a bit like tectonic plate boundaries on Earth, where you have icy crust spreading apart, and that has the potential to draw up material over sort of geologic timescales from below. So this simulation in the lower left, it's a computer simulation of what that might look like, and the kind of white and blue material at the bottom of the image is meant to be ocean fluid. So that is water from the ocean being drawn up and frozen into the ice shell over time and eventually exposed at the surface where we might be able to study it. And indeed, infrared data from Galileo spacecraft has shown that these bands and these regions that are kind of discolored here are associated with non-ice materials that we think is salt. So that's another good evidence that we're seeing some frozen ocean stuff there. I also just want to highlight that this work is being done not only by spacecraft. Galileo mission finished several years ago now, in the early 2000s, in fact. And in the kind of recent years, we've had a whole new generation of ground-based observatories looking at Europa, particularly Europa, and mapping its surface composition. Now, these give us much lower spatial resolution on the surface, but we can pick out features that we think are corresponding to certain salts on the surface. So this map on the lower left-hand panel was taken by the Keck Observatory in Hawaii, and the blue colors here just show the presence of table salt, sodium chloride, on the surface. Similarly, the Very Large Telescope in Chile mapped out the presence of magnesium chloride. This is another salt, and you can see it's here centered around certain regions of the surface. I should say that these maps show the entire surface of Europa, and the black shapes on there are geological features that we think are young regions of the surface. And magnesium chloride is a salt that we know forms in sea ice on Earth. So that's quite exciting. It seems like we are seeing the frozen version of the ocean. I'm just going to skip through these, just to say that some of the work I'm doing at the Open University is trying to understand the processes involved in this freezing of the ocean fluid and how that material might age as it's exposed to the space environment. So this is a Van de Graaff generator that we use to accelerate dust particles to about 40 kilometers per second to simulate the kind of space weathering that salts like that might experience, again, to better help interpret spacecraft data. So just with the last kind of couple of minutes here before I wrap up, I just wanted to highlight some really exciting new missions. As I said at the beginning, we're really at in our infancy of the exploration of these bodies, and there's a lot of exciting stuff to look forward to in the kind of coming decade or decades. We should be getting a lot of new information, and I firmly believe that the kind of revolution that we've seen in our understanding of the planet Mars over the last 30 years, this is about to take place with the ocean worlds. So first up, we have JUICE, which is the Jupiter Icy Moons Explorer, which launches in 2022, next year, in fact. I believe that's still on target. This is a European Space Agency mission. Its primary goal is to go into orbit around Ganymede, but it will also do 2 Europa flybys, and that's what this little image is kind of trying to get across in the top and the upper right, showing you some of the planned approaches to the planet, the moon Europa. So that will be taking a lot of remote data, mapping out the composition of the surface, some of these salts and things like that, and then ultimately going into orbit around Ganymede. We also have a NASA mission, another kind of NASA flagship mission called the Europa Clipper. Now this is really focused on just Europa, and it will do around 40 flybys. They've all been planned out already of the moon in its primary mission. And what it will do, what it will do is fantastic. It will image the surface, almost the entire surface, up to about 5 meters per pixel resolution, which is actually higher resolution than we have for a lot of Earth's surface, in fact. So we're going to get some fantastic images out of Clipper. It also has a dust capture instrument based on the one that was on Cassini, but an updated version of this. If we do see any plumes, then we can capture some of that material like we did at Enceladus. So that is going to arrive at the end of the decade, along with JUICE as well. We also have a lander on Europa, which is under development. It's not yet greenlit by NASA. We're not heeding the warning made by Stanley Kubrick and in 2001. And we are hopefully going to land on Europa at some point in the future. The landing site for this would be carefully selected based on results from those previous 2 missions to choose the best spot possible that has the youngest, freshest sort of ocean material exposed to the surface. But this is a challenging mission and will be one of the most expensive robotic missions ever launched. So we're waiting to see if that gets the green light. Further out, we have a really exciting mission to Titan to look forward to. This on the left, I just wanted to put this image in because it's another one of my favorites. You're actually looking through the upper atmosphere of Titan there at Saturn in the background. I think it's an absolutely stunning image from Cassini. Dragonfly, its primary goal is actually to study the surface environment on Titan. So where you have this hydrocarbon, methane, weather. That's really what it's there to look at, but it could also study regions where you might have ocean material from the subsurface delivered to the surface, like on Europa. And this is actually a drone. It will fly on Titan, so we're very excited about that. And finally, we also have a mission called Trident, nothing to do with the anything to do with nuclear defense there. It's just a coincidence in the name, but this is a mission that is hopefully, it's under review right now to be selected for NASA's next Discovery class mission. And this will go to Neptune's moon, Triton, to do a single flyby of Triton. That's very exciting because we have very little knowledge, very little data on Triton at this point, and it will be great to get some more. So fingers crossed that Trident gets selected. So there's plenty to look forward to there in the coming decades. And I just wanted to highlight as well that I really see this kind of teamwork, this interplay between spacecraft and Earth-based observatories continuing. They both kind of provide great complementary observations. So I think that's time for me to wrap up. So thanks very much for listening to me carry on about the ocean worlds. I hope that was interesting for you, and I will be happily take any questions. Thanks.
Thank you, Mark. That was extremely clear, excellent pictures. We've got a few questions. Mine was, where did the water actually come from to begin with?
So that's a really great question. I actually had a slide originally in the beginning of this to outline that, but it's worth just describing now. So we think that when the solar system originally formed, you have starting with the middle section nearest to the sun, the early sun, you would have had this gradient of material. So all of the water vapor in that kind of early dust cloud that would have formed the planets would have migrated outwards to the outer solar system. So the outer solar system would be much richer in water at that point. And gradually, as the planets form, you have material condensing onto surfaces, and that water is essentially just accreted much more readily in the outer solar system. So basically, these bodies formed with their water. A lot of it could have been moved around by impacts, but essentially just through kind of our understanding of planetary formation, outer solar system bodies tend to form with lots more water from the beginning.
And they probably keep it because it's further away from the sun as well.
Exactly, yeah. So it doesn't, unlike somewhere in the inner solar system where Mercury or the moon, I mean, the moon's very cold, of course, but if you're exposed to the sun on the surface of the moon, solid ice would evaporate, would sublimate away. You really need, in the inner solar system, you need an atmosphere to insulate you, to keep that water on your surface. So yeah, you're absolutely right.
Now, Eric has asked a sort of similar question, but where did the life come from, if there's any life?
Well, we don't know how life got going on the Earth. So that's a very good question. And I think if we had the answer to that, we might be able to predict a bit better where we would find it elsewhere. But at the moment, we only have very kind of broad guesses about where life could have started on Earth and how it could have started. So it's really by going and exploring places like these that we think could be habitable, i.e., life could survive there now. And if we go and explore them, we can ask the question, well, did life start there or not? And if it did, then that tells us that, oh, maybe the origin of life is somewhat common. But if it didn't start there, it tells us there's something special about the Earth that we need to figure out.
Okay, thank you. And another question is, what kind of signatures would you be looking for life?
That's a really great question. That's actually something that I'm actively researching. So we are focused right now on again, these two mechanisms for ocean water getting to the surface. So either trapped within these tiny icy grains in plumes, where a spacecraft might be able to capture them, or kind of frozen in to the salts in some of these these red bands you see on Europa here. They're very salt rich, and we think that if there is signatures of life, it could be trapped in those salts there.
You mentioned something about salty water. Is it sodium chloride, or could it be any kind of salt? Could it be potassium, something or other, sulfate or anything, or could it be, doesn't need to be salt, our salt?
It does not need to be our salt. You're absolutely right. Again, it's funny. These are really the big questions that we're trying to address right now. And another focus of my work. We actually have quite good constraints on the salts at Enceladus. This is Saturn's moon, Enceladus. Because of the plumes, because we had the Cassini spacecraft there until quite recently, we were able to get a good handle on that. And that seems to be a bit like Earth's oceans. It's sodium chloride. But we also have lots of kind of soda, like carbonate, in there as well. It's very alkaline. Europa, it's a bit of an open question at the moment. All we can do is look at the surface at this point.
Eric has asked the question, is there any scope for citizen science to play a part in this?
I think absolutely there is. I don't have any examples off the top of my head, but I think especially as we move into this new phase of missions, I think there's going to be a huge, overwhelming wealth of data produced by these missions that I think there's going to be absolutely loads of scope for it. There is also a lot of image data still to be processed from the Galileo mission, and Cassini. So I think absolutely, and I'd be happy to look into that and forward on any information that I can find about it. I just don't have anything to hand.
Lisa asked, could there be fossil-like evidence within the salt? I don't quite know. Is it fossils in the salt?
Yeah.
Yeah.
I understand that question. I think possibly that's kind of what we are looking for. We would expect at a place like Europa that any material on the surface that has come from the ocean is probably being delivered there very gradually over kind of a geological timescale, so many tens, hundreds of thousands of years. So yes, fossil really is what we're looking for there. Nothing alive, because the surface temperatures are very low. There's no atmosphere there. Europa is also bathed in radiation, so anything that is on the surface, we expect to be fossil.
Yeah, okay. Now, John has asked, thank you, Mark, fascinating. So what did it inspire you to do? What did you do?
Well, do you mean if it wasn't seeing Cassini?
Yeah.
It's a good question. I mean, to be honest with you, I just followed my interests one after another. My PhD project was focused on Mars. I was looking there at a very similar kind of salt and liquid water processes, but I was focused on Mars. And I just made the decision towards the end of my PhD that I needed to move in this direction because I saw these upcoming missions. I was absolutely fascinated by the data come back from Cassini. And so that was a conscious decision at that point. But I think most of the other stages I've just been following my nose to a certain extent. I've been lucky enough to be able to do that. And it's only in retrospect that I think back to that time at JPL in California and remember seeing the spacecraft at the time. And yeah, it does seem like there is a connection there.
Gordon Mackey asks, fascinating presentation, thanks. You mentioned a particle collector on the CLIPPER mission. What will that be able to tell us? Chemical composition or look for a biological material or life?
Yes, so that's a very exciting piece of kit. It's based on the design of a similar instrument on Cassini. This time it's called the Surface Dust Analyzer. I think they all have these very exciting names. It will be able to hopefully do both. It's got a very high resolution, chemical resolution, so we should be able to get all kinds of salt compositions out of it, but as well we should be able to recognize organic compounds if they are indeed there. So that's definitely one to watch.
Okay, now any more questions, anybody, other than my last one, which is not really relevant? Now, I know there was a mission in Antarctica, which is true to my heart, that was to drill down to, was it Lake Vostok or near, and I think they stopped it. Is that correct? I think they were getting worried about contamination because that was a sort of almost a practice session for going into things like Europa, etc., etc. Because you don't want, the problem is you don't want to contaminate things.
Absolutely. I mean, I think there's some lessons to be learnt from the Antarctic experiences, Vostok particularly. Vostok is very deep under the Antarctic ice sheet. It's a subglacial lake, for those that might not have heard of it. It was drilled into, I can't remember exactly how deep it is.
It's about 4,000 meters, I think, or something incredible.
Yeah. So actually, it is a good test run in some ways for the ocean worlds, because it is Enceladus. The thinnest parts of the ice crust on Enceladus are around 5 kilometers, so it's not too far off that. But the thing is, I think Vostok, the drilling process was halted there because of worries about contamination. The British Antarctic Survey went down a few years back and tried to drill into a similarly deep lake called Lake Ellsworth. They halted their attempt, not because of contamination issues, but just because of technical problems. They had problems with their pressure release system that they needed to drill and things. So it's very challenging to do this, even on Earth, with all the kind of logistical support that we can have here and teams of people and all the rest. So yeah, it's a big challenge.
Thank you very much. Thank you.
Thank you.
Rona, thank you very much for handling the question and answer session tonight. Some absolutely fascinating questions. I could just imagine us all sitting around having a pint or three and a chat and a few what ifs and a few debates, Mark. I think that'd be quite interesting. Can I just take this opportunity to thank you, Mark, for this most interesting and inspiring talk. That diagram comparing the Europa to Earth water amounts was a tad scary for me, and that there doesn't seem to be much water at all on our Earth, bearing in mind all the awful things us humans do to it.
Yeah.
Pre-COVID times, Mark, you'd be here with us receiving rapturous applause and a token of our appreciation and a thank you card designed and printed by Pauline. But we're going to have to send you them the old-fashioned way. Mark, thank you once again. I hope you can stay with us and experience the rest of our club meeting. There are some fantastic astro pictures coming up in just a wee while.
Yes, I will be hanging around for sure. I'm excited about it.
Excellent. Well, thank you. And now to the club news and Astro Picks this month. Dave is with us this month to show you what our club and our sister clubs in the north have been getting up to. He's got many stunning photographs taken by us amateur astrophotographers, and here he is to share with us all what we've been seeing in the night sky. Over to you, Dave.
Hey everyone, and welcome to the club news and photographs for April 2021. We'll start off with a bit of news. Paul Jenkins is going to be stepping down from the committee and we'll need to replace him, obviously. So a plea goes out to everyone for that to get in touch with the current club secretary or the membership secretary. And Paul, Eric's already said this, but we wish to thank you so much for all the work that you put into the club over the many years that have passed. Thank you again. Now you also see that Rona is heading off to the Antarctic to see the solar eclipse and will be stepping down from the committee and from her role as club secretary. That's an important and essential role, and we ask again that somebody steps forward to fill that empty space. Thank you, Rona, for your contribution over the years again. Next slide. Paul? Here we go. So what's going on in the sky? We've got the new moon on the 12th of April and the full moon on the 27th of April. And what it says here, the start of astronomical twilight, really means that our dark skies are disappearing and that there will be no true night. We won't get that full darkness. There'll be a kind of twilight. So already, in fact, way up to 9:30, 10:15, you can still see a bit of light in the far west. But that leads us to new opportunities to see things in the sky. If Paul, if you could maybe do me a favor and point out with your pointer the constellation of Cassiopeia for our members to help them locate it. We'll talk about Cassiopeia shortly when it comes to the. It's right at the top, Paul. Right at the top, about 1 o'clock. There we go. Cassiopeia, the favorite W shape, pretty much unmissable if you look to the. It'll be in the north when it's dark. And the other one is Lyra, which is at 10 o'clock. 10 o'clock, Paul? 11 o'clock maybe. There we are. Lyra for the next slide now. And that one's very low on the horizon, but as it passes into the later evening, it'll rise almost due northeast to east. Okay, next slide. Next slide takes us. Can we go to the next slide? There we are. So we've got the crescent moon comes up after sunset on the 13th and gradually rises higher into the sky. It passes through the Pleiades, quite close to the Pleiades, and will reach Mars on the 16th. And it's quite a close path to Mars, a very good photographic opportunity. And in fact, in Asia, it would be a true occultation, but here it'll just be a close pass. Interesting though. Next one. And towards the end of the month, we've got the Lyrid meteor shower. It's an annual meteor shower from the debris from Comet Thatcher, and between the 14th and the 30th of April, but that's when you'll see meteors at any point. But on the peak nights of 21, 22, 22, 23, that's overnight going into the dawn of each of these days. There's an average of around about 10 meters an hour, but that can be numbers much greater than that, and also much less. Now the radiant is close to Vega in the constellation of Lyra, which Paul just kindly pointed out to us, and that's where to look if you can find Lyra or Vega. It's not vital though. If you just look to the northeast, you'll see the meteors coming from that direction. So good luck with that. Next one. Next picture. Next, if we go to the next picture. So there we move on to our gallery of photographs, which everybody loves. Now we're going to start off with the next one. This one here is it's been of great interest to me when I saw this first. This sequence of photos is from Eric Walker's All Sky camera, which is a 24-hour-a-day camera pointing at the sky. It sees the entire sky from 360 degrees, but it was infiltrated recently by what's he's called Henrietta, I thought it was spiders from Mars, but it turns out to be spiders from just Common Bridge. Friendly though this thing is, it's going to have to go because it's creating a web across its camera lens, something like a Sky network of Starlinks. Okay, so bye-bye Henrietta, that's the last we'll see of you. Next slide. It captured another moment in time here when an aeroplane flew past. You can see its navigation lights flashing there against the starry background. Here's an interesting thing. A meteor or a flaring satellite, it's difficult to tell. Because these things are time-lapsed and record over a few seconds, you'll see that that's a bright light which has come from nothing and diminished to nothing, but is brightened up in the interim. So it's either a meteor flaring or that's a rotating satellite catching the sun. So could be either. Nice picture though. Next one. And this is, we weren't sure what this was to start with because it looks like something coming across the sky and then flaring up dramatically and then passing again into obscurity. It turns out, however, that this was the Scottish Air Ambulance helicopter en route to Rigmore Hospital, and that's its landing light. Next one. Okay, now I think we've got a short video of the International Space Station passing. There it goes. And here it comes again, crossing Eric's garden. And again. Fantastic. Now, it's been a great month for the moon. We've had lots of opportunities to see the moon almost from its start from new. This picture was captured by Von Hare down in Perth, and it captures both the Earthshine, which is the illumination of the dark side of the dark part of the moon, not the dark side of the moon. But she's also captured an interesting thing, which is what's called here beads in space. They are on the lower left. They are very, very high mountain tops or the tips of pointed craters. They're so high that they're catching the sunlight whilst their bases are steeped in shadows. It's rare to see that. Very, very interesting. Off to the next one. And I took this picture pretty much on the same night. So I've just taken the exposure for the moon not to show the earth shine. There's too much of a dynamic range. When you're taking a photograph of the moon, it's really difficult to photograph both of these things, because if you try and catch the earth shine, the brighter part of the moon ends up being overexposed. But you can see these beads in space again, just at the lower tip, and the Sea of Crises showing really clearly there in the middle. Next one. And this is a close-up of the same thing. You can see just how high these tops of these mountains must be in order to be illuminated that far into the dark part of the moon, just on the tip there. Next one. And this is the moon just a day older. You can see now that the sea has moved across. There's more of the moon illuminated, and again you can see some nice detail in there. And the next picture, there's quite a lot of these, so we'll do. There's a much closer picture of that crater and the sea there. Just let you have a look at that for a wee sec. These pictures are clearer because the seeing conditions, the stability of the atmosphere was really good that night, so you can get much closer. The next one. There you go. You can see that we've got the moon much earlier than the day. This was photographed in almost in twilight, and it softens the features dramatically on the surface when you take a photograph of it. Next one. Now this region of the moon here is called the Theophilus region because of the crater at the top there is called Theophilus. And this was the subject of a detailed look at the moon that we hosted one of our live webinars on. We had myself, Eric, and Pauline McRae, and we did a live session with the telescope at Conan Bridge and had a glorious night of looking at the moon in great detail. And I really hope that people can join into these webinars. We're going to do a lot more of them as the summer passes on, doing sunspots as the solar activity increases. But if you want to see that particular episode of the live webinar, it's on YouTube, and you can find links to it certainly on the Highlands Astronomical Facebook page, and I think it might go into the Stargazy Pie this month. Next one. Here's a super picture of a Eratosthenes crater taken by Eric Walker. You see some lovely detail on that. And one of the things that we spent quite a lot of time discussing were these collapsed areas of terracing, which is on quite a number of the lunar craters. You can see there that those clearly show up in that photograph. Next one. Right, and another photograph of Eric's previously of the crater Tycho, Clavius, and the straight wall. Usually these features are quite difficult to see, particularly the straight wall only shows up at certain phases where they've got shadow on it. Clavius is a very interesting crater. As you can see there, the floor of the crater is dotted by what looks like a ball that's bounced across it, diminishing in size from one side to the other. And Tycho is the one with the enormous rays that spread most of the way across the moon, but they don't show up at that aspect when you need the moon to be nearer the full before you can really see the effect of that. Next picture. There's a marvelous picture that Eric took earlier of the moon and turned it on its side so that it gives a much more dramatic aspect to it. You can see Tycho on the right there now and how far the rays spread from there. Next one. Pauline's been busy taking photographs. She's just got herself a new camera set up and a little Ioptron star tracking system for astrophotography. And these are some of her early attempts. She's got Mars and the Pleiades, or Seven Sisters. You can see those Seven Sisters just on the right there. And the asterism of the Hyades off to the left with Aldebaran, the Eye of the Bull. And the wee orange one under the Pleiades is obviously Mars. Nice picture. Next. And here's one I took of the same thing. And you'll see that she's managed to capture Mars as a disk, whereas my picture of Mars is in the bottom there. It looks more like a star. And that's because it's a slightly longer exposure and the aperture on the camera has been stopped down and it creates diffraction spikes on the stars. That was a really interesting conjunction there. And on to the next one. Eric managed to capture a picture of M35 in Gemini. And you can just see it there. This is a very wide aspect of the sky. And the entire constellation of Gemini is visible. If you draw the lines, you'll have to see where they are. The brightest stars are Castor and Pollux, and M35 is down at the tail end there. That's a really, really nice star cluster, especially for astrophotography. Really, really clear, quite a wide aspect to it. Next one. And he's done a great job here because he managed to get M36, 37, 38 and 35 in Auriga. So he's got M35 further down, and up in Auriga he has captured these. These are just open star clusters, but good binocular objects. You can see all of these things with binoculars. Next one. And here we are with Orion, and that's the whole constellation of Orion. So Betelgeuse at the top, and Rigel at the bottom right, and he's got the M42 Nebula just right in the middle of the wee sword there. Great picture. Next one. Now these are pretty amazing pictures, I have to say. These are taken by Mark Waugh, and he's got the Elephant's Trunk Nebula. This is a seriously long exposure and probably assembled by over a number of evenings, certainly over a number of hours of collected data and then a bit of processing. And I suspect that that's also shot through a hydrogen alpha filter to create that red effect. Next one. And this is definitely a picture taken with a HA filter, hydrogen alpha filter. And that red color is not something that you could see in a telescope, but you certainly see it once it's exposed through that filter, because it actually is genuinely that color. That is emission in the hydrogen spectrum, and it only shows up in a photograph. Next one. And now he's added an extra filter to bring out the other composition in the same nebula, which gives you both the hydrogen and S111. Not quite sure. I think that's sodium, but most likely sodium. Fantastic image, almost three-dimensional. You can see the stars in the middle there look like they're embedded in that cloud of dust. Next picture. And he's captured Thor's helmet. This is a Wolf-Rayet star in the middle of a cloud of molecular gas. You can see that the star is kind of pushing the gas away from it, creating what looks to be like a bubble. That's a very, very difficult thing to see. It's not, even in a telescope, that's virtually non-existent. These are all deep sky astrophotography targets for long exposures. Well done, Mark. Next one. So welcome to the CASI Nova Club. And as Eric pointed out, not the Casa Nova Club, the CASI Nova Club. This is a new star that's emerged in the constellation of Cassiopeia. And it was spotted back on the 18th of March by a Japanese amateur astronomer. And the stars flared up from, there's no sign of anything there before, and it suddenly came up to about the 10th magnitude and then remained for the last week or so at 7 magnitude 7. So it's easily seen with a pair of binoculars. Only if you know where to look, though. It's a tricky one to find, I must say. Star charts, I didn't really make much progress with. Identifying which star is which is very difficult. But the binoculars and a photograph, or a telescope and a photograph, I thought was the best way to find this. So if you were to find M52, which you can look at a star chart for, and then find that with your binoculars, you'll see the space marked by the red circle, which at the moment has no nova in it. If we go to the next slide, we'll see here that on the left-hand side, the aspects changed somewhat there. This is a much closer view, but Eric's caught this. M52 is to the top left there, and then there's a row of brightish stars underneath that, and then the nova is right underneath those ones. Next one. Next picture. Right, so there we are. That's if you turn that on its side slightly, you can see there's no star where the pointer is, but there's a bright star next to it. And the next picture she'll show you. Next picture. There, we've got the M52. We've got that line of stars, and we've got the nova. It's right next to a star, so it's fairly easy to spot once you get it. It'll take a while to actually find it, but once you do find it, you'll keep going back to it quite easily. So that's the first nova I've seen since 1973, when there was a nova in Delphinus, the dolphin. So look out for that. It's a great one for your binoculars and wee telescopes. Next picture. And here's Pauline. She got her new camera set up out and about and got this one. This is a much wider field. You can't actually see the M52 star cluster in this one, but the position that she's indicated for the nova is the correct one. Next one. And again, this is a close-up that Pauline took. It's an enlargement of the same photograph, but you can see that the box that's in the right-hand side matches her her photograph, so she's accurately found and identified the nova. Super job, Pauline. Well done. Next one. And Mick O'Donnell from Sigma, he's done precisely the same thing. He's identified it using the stars. He's got 4 Cassi, Calf, and then these much smaller stars are indicated by star map designations. Great photo. Next one. And Dennis Buczynski has caught the same one. There's a wee circle there with the nova in it. He's also captured the Babel Nebula, which is off to the red nebula off to the right hand side of it there. That's an amazing picture. Astonishing number of stars in there. You can see what I mean about using a star chart. If every one of those stars was recorded on a star chart, it would be nigh impossible to find anything in there. But a photograph will match what you see in your telescope. Okay, next picture. And now we've got some aurora. There was quite a lot of aurora over the month of March. and lots of people caught it. It was difficult here because there weren't that many clear spots amongst the clouds to see it, but up in Orkney there certainly was, and I think Eric managed to capture a few opportunities as well. So if we just run through these ones, we can have a look and see what we've got. We've got Sue Shackleton's one. This is from the North Roncy Astronomical Association. Got pillars in this one. And again, Eric's caught. You can see just a glow in the horizon there from Cromarty Bridge. And from Conan Bridge, he's got a slightly better. Sue's got another one from North Roncy. Marvellous. Overlooking Rousey. And this one here, if we could just stop on this one, Ian Hall from North Roncy has sent this one in, and he's caught on this this big red bow on the corner of the green parts of the aurora, and that is in fact not it's not an artifact of the camera or processing thing. That is a true color from the aurora. They can go entirely red and change the sky to, they can go from green to becoming completely red. It's called an auroral corona. So there's a true picture of red in the aurora. That's a super picture. Next one. I've got a time lapse here over Skye. That's of the aurora. Splendid. Now, since the stars are going to be disappearing for a while as the summer months come on, and I think, you know, by the time the end of this month, there won't be much opportunity for deep sky astrophotography or general, you know, looking at galaxies and nebulas, because the light will just be too much for it. So we're going to concentrate a little bit more on the sun, and we'll be doing webinars, live webinars of sunspots as we come out of solar minimum, and there's more activity day by day now. There's a wee tiny spot today. There were some spots a couple of weeks ago, and with a short gap of a few days, but as the weeks go by, there'll be more and more opportunities to see sunspots. So how to do that, if we go to the next slide, you'll see that this is what you can do with just a camera and a telescope. This is a white light filter on the end of the telescope. You've probably seen that in the last picture. And that cuts out 96–97% of the light from the sun. And you can safely look through the telescope at the sun with this special filter on it. If you do not have a filter, you must, of course, never look at the sun with it unprotected. But you can do it by projecting the image onto a piece of card. You can do it with binoculars. In this diagram here, it shows you that covering one of the lenses on your binoculars with a piece of card, make sure that that's nice and secure. Then point the binoculars at the sun with a card underneath it, and move the binoculars up and down until you get a clear image of the sun on the card, and you'll see sunspots on that quite clearly. So that's projection with binoculars. Same thing for a telescope. And do it in stages. It says here at the bottom, make sure you move the binoculars away every few minutes. You can damage them if you prolonged sunlight going through them. It can crack the lenses if it's, and I wouldn't do it on a reflecting telescope either, because it heats them in dramatically. But a refractor is a good thing to project the sun with. So thank you very much indeed for wading through all these photographs. I must make a plea to everyone, if possible, to submit more pictures. The more we have, the more variety of pictures we have for these sessions, the better. I look forward to seeing your photos in the future. Thank you very much.
Well, Dave, thank you very much for that. That was absolutely amazing. And what an amount of photographs we received over the past month. I also know there were many more that you could have presented.
Indeed. Well,
but we'll save them. We'll save them for next month. Yeah.
Well, it's 20 minutes past what we were supposed to be doing anyway. So.
It's a great part of the monthly meeting that day. So I don't apologise. Once again, just can I say thanks to all the contributors in our astronomy clubs and groups across the north of Scotland, and for their permission to let us show them. They're wonderful things. Wonderful things. Right, guys, that is just about us for tonight. The night may be finished for some of you, but if you want to join us for a wee informal blether, just click on a link which should be shown in the chat box. I think Rona put a link up a short while ago, and I'm hoping, oh, Rich has put one up as well. So you can click on that link. After you've clicked on it, you'll see a screen or a box telling you that the meeting is about to start. It's going to take Rich a couple of minutes to close down this meeting and open the chat room that we're all going to. So just hang on until it does. It will open, you know, so just be patient. But can I just say thanks to all of you once again for coming along. And until the next time, clear skies and keep looking up.